is a regression? So regression basically it's a statistical method which we can use to show the relationship between the dependent or a response variable with one or more independent variables or the predicted variables. Over here, y is representing the response or a dependent variable, where x's are basically representing the predictor variables or input variables, or we can say that independent variables. Okay, or input variables. So this regression analysis we can use to predict the dependent variable based on at least one independent variable. Okay, so it might be possible we have one independent variable or more than one independent variables. So based on those independent variables, we can predict how much changes will be occur in the dependent variable. Okay. Similarly, we can explain the impact of the changes in the independent variable on the dependent variable. So there are two types of the regression analysis we are going to discuss. So first of all, we will talk about the simple linear regression, which I am going to talk about in this particular video lecture. Whereas we have the multiple linear regression, we will talk about in the next video lecture. Okay. So when we are saying the simple linear regression, that means we have only one dependent variable and we have only one independent variable. So remember that in a simple linear regression as well as in a multiple linear regression, the main thing is your dependent variable must be a measurable or a quantitative variable. Okay, but your independent variable could be measurable or could be a binary form or a nominal scale or ordinal scale, right? But your dependent variable must be in a measurable form. Okay, so let's talk about different types of relationship. So over here I'm showing you the different scatter plots. Okay, like on x-axis, on y-axis. So x-axis is basically indicating the independent variable, y-axis is indicating the dependent variable. So these dots are basically representing the values of x and y. This black line is basically indicating the relationship between these two variables. Okay, so as we can see that this scatter plot is indicating that x having the positive relationship with y. As x increases, y is also increasing, and they have the linear relationship right now we are indicating. But we can see that there is a much gap of these dots from the regression line, so we can say that it might be possible this contains lot of variation. Maybe this regression line may not be accurately predict would be able to accurately predict compared to this line, because in this particular line, although x and y have the negative relationship, as x increases y decreases, but the dotted dots from the regression line is quite narrow, so that means this regression line would be able to predict it accurately. So which means in regression analysis, our ultimate target is to predict such line or to identify the such linear line that the gap from this point to this point should be minimum. So that means from every particular data point, the regression line, the gap is must be minimum, which is also known as the error. So this term is basically known as, this gap is known as error. Okay, because this dot is basically actually representing the actual values, whereas this black line is representing the predicted value. So the gap, that is the original value minus the predicted value, is known as the error. So in regression analysis, the ultimate target is how we can reduce this error. However, we would be able to find out the best fitted linear regression line. But it is not compulsory that the relationship between the two variables is only the linear. It could be non-linear. It could be a strong relationship. Okay, it could be a weak relationship. Although they have the linear relationship, but could be strong, could be weak, could be no relationship. Okay, so obviously we are talking about the linear regression, which means we are talking about this one, this one, this one, as well as this one. And we are talking about that we want to find out such a linear regression, such a linear line which would be able to predict that particular data in a very appropriate manner. Okay. So now, first of all, we will talk about what is the simple linear regression model, and then we will discuss how we can estimate the parameters model using the method of least square approach. Okay. So first of all, let's discuss what is a simple linear regression. As we have discussed earlier, in a simple linear regression, we have one dependent variable, one independent variable. The dependent variable must be in a measurable form or a quantitative variable. Okay, or we can say that it should be a ratio or an interval scale variable, whereas the independent variable could be a numerical, or you can say the quantitative variable could be the attribute, perspective, or ordinal, or a nominal scale. But generically, when we are talking about a simple linear regression, both the independent variable or the dependent variable must be the quantitative variable. Okay, so this beta naught is basically representing the intercept value. Okay, this beta 1 is known as the slope of this regression line. It is also known as the regression coefficient of this regression line. This E is representing, or you can say this is basically representing the error term. Okay, so now we want to find out the values of beta naught and beta 1. However, we should be able to minimize this one. Okay, so let's represent this regression line in a scatter plot. So on x-axis we have the independent variable, on y-axis we have the dependent variable, which is y. Okay, against every x we have plotted the value against the value of y, and we have find out the regression line. You can say that, so there could be the multiple regression lines. Now our target is we should find out such a regression line that this error should be minimum. Okay, so which means, as I have told you earlier, that this epsilon is basically representing the error. So this blue line is basically, let's say this is a fitted regression line. So the gap from this dot to this regression line is basically known as the random error. So that means we want to find out again such a linear regression line that this error, this gap between these dots and this regression line should be as less as possible. Okay, so this beta 1 is basically indicating the slope of this line. Okay, and obviously this beta naught is representing the intercept point where this regression line is going to cross this y-axis. So which means ultimately we want to find out the value of beta naught. So that means the fitted regression line, or you can say the value of beta naught is b naught, and the value of beta 1 is b1. So either we can represent b naught with b1, or either we can represent that b naught hat or beta 1 hat. So these are the estimated values. Okay, remember that. So these are the estimated value, but as you can see that in this particular regression line there is no epsilon value. Okay, so remember that when we are estimating this regression line, we will assume that this error term is normally distributed with mean 0, okay, and standard deviation 1. So that means a normally distributed with mean 0 and 1. So that's why we can eliminate this error term while we have estimated this regression line. We will assume that there is no error, okay, mathematically, or you can say theoretically. So how we can do that? So in order to minimize this error term using the method of least square, so how we will do? So the actual values we know that that is representing with y. Okay, whereas this blue line is represented with the estimated regression line once we find out the value of beta naught and beta 1. So the gap between this one is called as error, right? This is error. So what we want in a method of least square, that the sum of square of error, that is this one, must be minimum. Okay, so that we are going to representing over here. So we want to minimize the sum of square of error. So y hat is can be represented over here. So if I open it up, okay, we can write down like this way. Okay, now in order to find out the value of beta naught and beta 1, means what kind of the formula we are going to use to find out the value of beta naught and beta 1, so we can apply the method of least square. And what is the method of least square? We are going to differentiate this function with first beta naught and then beta 1 in order to find out the values, and we will equate those equations equal to the 0. Okay, so let's first differentiate this function with beta naught, and when we are going to differentiate this one, as we know that the power comes first, that is 2, and then the straight function. Because we are partial differentiating with respect to beta naught, this value would be 0, this value is also would be 0, and this function would be when we are differentiating with beta naught, the answer of this one would be -1. So we will get this equation and we will put it equal to 0. Okay. Similarly, now we are going to differentiate the same function with the with respect to beta 1. Again, 2 will come first. Okay, this would 0, this would 0, and this would be minus x1. So we have x and minus. Now we have two equations. Now we are going to simplify these equations. So once I have simplified this equation, I will get this one. I have simplified this equation, I will get this one. Now in order to find out the value of beta naught, what can I do? I can use this first equation, that is n beta naught hat would be equal to summation yi, where I is 1 to n, minus beta hat 1 hat summation I from 1 to n xi. So if I divide it with this particular n, this is n, this is n. So that means beta naught hat would be equal to this one, or we can say that this is equal to y bar minus beta 1 hat into x1. So this is the formula of beta naught. Now we have to put this formula over here, means this one, and now we can find out the value of beta 1. So I have already done this. So this is the answer of the beta naught. This would be the formula for beta 1 in order to find out the best values of these parameters, or you can say estimators. Okay. However, our error will be minimized, or you can say the residual will be minimized. So it's up to you whether you can use this particular formula or whether you can use these formulas, okay, in order to estimate the values of beta 1 and beta. Okay, now let's discuss that instead of performing it manually, how we can do this simple linear regression through R, and then we will try to interpret the results. Okay, the example I am going to take is that, let's say I am working in a record company and my boss is interested in predicting the album sale from the variable advertising. Okay, so he is interested that if we are going to invest more and more in advertising, whether our album sale is increasing, decreasing, or it has no effect. So this data set is available. Okay, so let me open it. So this is the album sale data. Okay, now I am going to first of all reading this data set. So let me uh, increase the size of the font. Okay. Okay, so first of all, with the help of this particular command, I am going to read the data, because this data is already available in the same folder where I have created this particular project. Okay, so let me run this command. Okay, as you can see that with the help of this particular command, I am able to reading the entire data set. Okay, so that is the name of the data file. Header is equal to true, mean that every column first thing would be considered as the name of the variable. Okay, so now I can view this data set. As you can see that we have the two variables, one is advertisements and other one is sales. Now in order to fit this simple linear regression, let me first run this command. I am skipping this particular command. Why I am skipping, I will let you know later. Let's first run the simple linear regression. As you can see that our dependent variable is sales, and then we can use tilde sign, and then we have the adverbs. Okay, that is basically the our independent variable, and the data is in our variable, that is album1. So if I run this particular command, so simple linear regression is fitted. Now in order to see the result, we have to use this function summary album sales dot one in the variable where the results are available. So as you can see that we have this output of this regression line. So you can see that the values of the betas are basically in the form of scientific notation. So if you do not want to see this scientific notation, you want to see in the decimals, then first of all you have to run this command options sciping is equal to 99 and then again run these commands. Now you can see that the answers are in a decimal places. So let's find out that what thing we can get from this linear regression model. So the first task of R is that we want to find out the values of B naught plus B1x. So B naught is basically the intercept value, which is basically this one, which is 134.13. So the value of B naught is 134.1399. Okay, plus the value of beta 1 is 0.096124x. Okay, that is this one. So which means this is indicating the sales, this is indicating advertisement. Okay, right? So we can see that the advertisement has having the positive effect. So as we are going to invest, let's say if I am going to invest $1 in the advertisement, this much my sale will be increased. Okay. Now, once as we can see that there are different data results we are also uh, we have in the output. So now let's see what these results are indicating. Okay, first of all, we are interested to find out the value of the coefficient of determination. Why we are interested to find out the value of the coefficient of determination? Because the coefficient of determination is able to tell us how much variation the independent variable can explain in the dependent variable. Okay, so which means in terms of the regression, R square, which is the coefficient of determination, the formula for that one is the sum of square of regression divided by sum of square of total. Okay, so how we can calculate this one? As you can see that the sum of square of total can be partitioned into two portions. One is the sum of square of regression, and the other one is sum of square of error. And how we can calculate the sum of square of total, how we can calculate the sum of square of regression, and how we can calculate the sum of square of error. Okay, this is also known as total variation, explained variation by the regression line, or you can say explained variation by the independent variables that are available in the model. And this is the unexplained variation, that is the residuals. Okay, so over here we have seen this thing in the picture form, where this blue line is basically the average of this y variable. This is the fitted regression line. Okay, this is basically the actual, or you can say the observed value, which is of y. Okay, from the observed value to the fitted value, the gap is basically known as sum of square of error. Okay, this is basically the residual value. Okay, whereas the gap between the fitted value and the bar is basically the sum of square of regression. Okay, that is basically how much variation this regression model can explain in the dependent variable. Okay, or you can say how much variation the independent variables can explain in the dependent variable. So this is the total variation, that is from observed value to the average value. So R square would be able to tell us, as I talked about earlier, that how much variation the independent variable is able to explain in the dependent variable. And as we know that the coefficient of determination is always lie between 0 and 1. So now as you can see that the same output which I have shown you earlier, that over here we can see the answer of R square and adjusted R square. Okay, so the value of R square is indicating what? That is indicating that 33.5% approximately, or we can say that 33.46% of the variation in the album sale would be due to the advertisement. Okay, or you can say that advertisement can explain 33% or 33.5% of the variation in the album sale. So remaining 67% of the variation we don't know. So what other factors may influence your you can say the album sale. Okay, so right now only 33.5% of the variation your independent variable, which is the advertisement, can able to explain in the dependent variable. So right now, because we have only one dependent and independent variable, so that means with the help of the R square, we can find out the correlation coefficient, that is 0.5784. Okay, how we can interpret that one? That means almost 58% of the time when uh, we have invested on the advertisement, album sale also increase, because this is a positive correlation. Okay, now the next thing is we have talked about these estimates. We have talked about the regression R square. So what about the adjusted R square? Basically, this is the interpretation will be the same. The only advantage of the adjusted R square is because normally people are saying that the R square value will start increasing as you will be start increasing the independent variable. So that's where they adjust use the value of adjusted R square. So they just you can say fix this increasing number of variables in the formula. So the interpretation will be the same. So how we can interpret it? That 33% of the variation in the album sale, the advertisement budget, or you can say, can explain the variation in the album sale. Okay. Now we want to find out, or you can say, because these are the descriptive values, we want to perform the inferential analysis whether this relationship between the sales or the advertisement is significant or not. Similarly, we want to see that because R square is indicating the goodness of this regression line, whether this fitness of the regression model is significant or not. Okay, or we can say that whether the advertisement expenditure is significantly able to explain the variation in the album sale. Okay, so how we can do that? First of all, let's test it whether this beta naught or beta 1 are significant estimators, okay, or the values are significant or not. And then with the help of F statistic, okay, we can say that whether this regression model is good enough or not, or you can say significant or not. Okay, so for that the formulas we are going to perform is these three tests. Okay, for beta naught and beta 1 we are going to apply the t test. Okay, basically our already applied these tests, as well as in order to check the significance of the regression model we will apply the F test. So theoretically, in order to test the slope, how we can write down the null and alternative hypothesis. In order to test the intercept, how we can write down the null and alternative hypothesis. So right now, because there is no value is given of the beta 1, so we are going to use is as 0. That means our h naught will be that the slope is equal to 0, which means there is no relationship between the independent variable and the dependent variable, or in our example case, that means there is no relationship between the expenditure, advertisement expenditure, and the album sale. Okay, or you can say there is no effect of the album advertisement expenditure on the album sale. Okay, whereas alternative, that is not equal to 0, that means there is a significant relationship. Okay, or you can say there is significantly the advertisement budget expenditure is able to explain the variation in the dependent variable, or there is an effect of the advertisement budget on the album sale. So for that we can use test statistics for the slope over here, and this is how we can find out the test statistics. These are the critical regions. Similarly, in order to check the significance of the regression model, what is, because right now it's a simple linear regression, so that's why this will be the same. But if it is the multiple linear regression, then we have to pick F for all the betas that are related to your independent variables. But right now, because we are dealing with a simple linear regression, so there will be beta 1 is equal to 0, or there is a beta 1 is not equal to 0. So which means beta 1 is equal to 0 means this model is not a significant significant model. Okay, whereas beta 1 is not equal to 0 means this model is a significant model, or you can say the independent variable is significantly able to explain the variation in the dependent variable. So this is how we are developing theoretically, but let's see this thing in the R output. As we have already calculated, this is basically the beta naught test statistics. Okay, this is basically we have performed the test statistics or inferential analysis on the slope. As we can see that both are less than 0.01, so this is indicating that the album sale can be significantly predict with the help of the advertisement budget. So which means advertisement budget is a significant factor who can batterly or significantly can explain the variation or can affect on the dependent variable. Similarly, this F test statistics is indicating that larger the F, better the model is. Okay, so larger the value of F test statistics, better the model is. As well as we can see that this p value is less than 5%, which means reject X naught. That means the overall prediction of the album sales based on the advertisement budget is significantly well. Okay, I hope you got the idea that how we can interpret these results. So once we have fitted this linear regression, now we need to check the accuracy of this regression model. So in order to check the accuracy of the regression model, we are going to perform three things. Number one, first of all, we are going to identify whether is there any particular data point which can affect our regression model. So which means is there any outlier in our data? So if we are going to delete that outlier, whether our regression model is going to be effect or not. Okay. So for that we can use these techniques. Okay. And then furthermore, we will talk about that the errors that was due to the estimation of the regression model should be independent. Okay, so they are not depending on each other. So the assumption of independence of error we are going to test with the help of Durbin-Watson test. And lastly, we have to check the assumption of about the residual regarding that the errors or the residuals must be normal and there must be homogeneity in the variance. Okay, so let's first talk about obtain the case-wise diagnostics. Okay, regression deletion. Okay, that means there are some rules available which we can use, that if particular data point is violating these rules, so we can delete that data point, or you can say that case. Okay, and then after deleting that case, we again run the regression model in order to see whether our regression model fitness is still significant or whether the coefficient of determination is improved or not. Okay, so before testing this one, let me go again to the code. Okay, so I have also applied basically the confidence interval as well, because we can also use the confidence intervals in order to test whether our parameters are significant or not. Okay, as you can see that I have finding the confidence interval, okay, of the variable album sales dot one, in the variable in which we have the fitted regression line. So if I run this command, so this is basically by default using the 95% confidence, which means alpha is 5%. So this is lower confidence interval of beta naught, this is upper confidence. This is lower confidence interval of beta 1, this is the upper confidence. So how we can interpret it? As we have seen that the value of beta 1 is h naught is 0, where our alternative is not equal to 0. If the value of beta 1, which is 0, is lying within this one, we will say except h naught. If the value of beta 1, which is equal to, is not over here, then we will say reject h naught, because the value of h naught, that is beta 1 is equal to 0, is not lying within this range. So we will say reject h naught. That means again the advertisement budget has significant relationship or you can say significantly affecting the album sale. Okay. So if you want to find out the confidence interval on 99%, which means the alpha is 1%, okay, so you can use this particular command. So still advertisement budget is significant. Now let's diagnose it. Okay, that means first of all we are going to obtain the case wise. But before running the R code, so let's discuss first one by one. First of all, we are going to talk about this thing. Okay, that is basically obtaining the case diagnostic. So for that, we have the techniques of standardized residuals, cook distance, leverage, and covariance ratio. Okay, first of all, obviously, in order to identify the outliers or influential cases that can influence our regression model. Okay, what I am saying again and again, outlier or the influential cases. Let's say this is x-axis, this is y-axis, and we have this regression. You can say scatter plot, and we have fitted the regression model. And suppose one of the dot is over here, so now we want to see that whether this dot is significantly affecting our regression model or not, whether this dot is the outlier, okay, or not. Okay, so how we can do that? The first criteria is we can use the standardized residual, and there are some general rules. Okay, what are the general rules? That no standardized residual should be more than 3. Okay, so you can generically use it that the standardized residual values should not be more than 3. The other one is that if more than 1% of our sample cases are greater than 2.5, then there is evidence that model is fairly poorly fitted. Okay, so that means if more than 1% of the data points are more than 2.5, having the 2.5 standardized residual, so then we cannot rely on the fitness of the model. Similarly, if more than 5% of the cases are more than 2, you can say standardized residual, then there is also the evidence that model is poorly fit. So instead of using all, mostly people are saying that you can use this basically concept, which is basically the third one, that you should check that at least 95% of the cases must having the residual within plus minus 2. Okay, so if that is the case, then we can say that our model is good. Okay, so furthermore, because the problem with the standardized residual is that do not provide a particular case influence on the model. So it is just talking about the, as a whole, that whether we model is good or not. Okay, they provide the criteria with the help of 1% or the 5% perspective. So if we want to find out the perspective of the individual cases, then we can use the cook distance or head value, which is also known as leverage, or we can use the covariance ratio. So basically, Cook in 1982 gave us that if the value of the Cook distance is greater than 1, then that is the concern that you should uh, delete that particular case or that particular data point. Okay. Whereas the hat value is always lying between 0 and 1, where 0 means that there is no influence of the particular data point, or you can say case, whereas 1 is indicating that it has purely influence of the overall on a overall prediction. So first of all, we have to calculate the average leverage value. How we can do that? That is k plus 1 divided by n, whereas k is representing the number of independent variables, n is representing the number of data points. Okay, there is a cutoff point that is basically provided in 1978 as well as Stevens in 2002. So they gave us that we have to investigate the cases which are greater than this one. Okay, that means we should delete those cases according to them if certain cases having the leverage value more than twice of the average. But in 2002, Stevens says that we can he recommended that we should delete only those cases which are 3 times of the average of this value. Okay, So based on this average level value, we can find out the covariance ratio. Okay, so how we can do that? This is the formula to find out the upper covariance ratio. This is the lower covariance ratio, and we can see that if any of the case or the data point are crossing these lower or upper confidence limits, you can say upper or lower limits, then we can delete that particular case. But generically, what most of the people are recommending that you should only see the cook distance. Okay, like Stevenson in 2002 says that you can identify the significance of the outlier of any particular data point if the cook distance is greater than 1, but it is less than 1, there is no real need to delete the particular data point. Okay, so which means based on only the cook distance we can decide whether the particular case or the particular data point is outlier in our case or not. Okay, so before discussing the next thing, so let's perform this thing in our R. So first of all, with the help of this command, what I am going to do is I am going to find out the cook distance. So basically I am plotting the cook distance. So this is the name of the variable in which we have fitted the regression line. This is basically indicating the size of the, you can say, dots. Okay, we are saying that dot should be red color, which c is equal to 4, that is basically plot number. So in this plot, which is equal to c is equal to 4 is basically the cook distance plot. So if I run this command, okay, so let me run it again because it is creating some. Okay, now as you can see that this plot is indicating the cook distance plot. So this is the data points on x-axis, y-axis we have the cook distance. As you can see that 0.1, 42, 169, even all the data points, so they have the largest cook distance. Okay, but all the cook distances are less than 1, which means there is no outlier case in our data set. So if any of the data case is greater than 1, so we have to delete it and then again fit the regression model in order to see that whether the still our regression model is significant or not. So furthermore, if you are interested to find out the values of the residue, so basically with the help of this command R standard, so I am finding the standardized residual value. With the help of this command, I am finding the cook distance against every particular data point. With the help of this function, I am going to find out the hat or the leverage value, and with the help of this function, I am going to find out the covariance ratio. So all these things I am going to store in different variables, and then all these variables I am going to save in the same variable in which we have store our the data. So basically in the variable where we have all the data sets. So for that I am using the function drive.table and the name of the variable in which we have already entire data set. Okay, and then I am mentioning that album sale data with after diagnosing the outliers. Okay, and then I am mentioning separate with the tab sign, row name is equal to false. Okay, so let me run this command. So with the help of this one, it is going to save up this particular file in the folder where you have created this project. Now I am going to round this data up to 3 digits. Okay, now as you can see that all the data set is in the round of up to 3 digits. Okay, so now I am applying the standardized residue criteria in order to find out the error. So over here I am giving that if the standardized residue is greater than 2, or you can say with the help of this or sign, or less than -2, so eliminate those ones. So which means if I basically run this command, as you can see that it is showing me all the data set with true and false. So the true means yes, they are you can say having the standardized residue more than 2, whether it's positive or negative, minus negative 2, mean less than -2 or more than +2. False means they having the standardized residual is within the range of -2 to +2. Okay, now what I am doing is I am storing this basically command into the variable, and then I am summing it. So basically, out of all the data set, the total standardized residual, so there are the 11 data points which are having the standardized residual more than +2 and less than -2. Okay, so now let's display this data set with the variable sales, advertisement, as well as the standardized residue. So I am accessing this thing with the help of this particular command. So if I run this one, as you can see that we have the sales, advertisement, adverts variable, and then the standard residue which we have stored in that particular data. Okay, basically we have stored hook distance in that data, leverage value, and hook, you can say the basically ratio, that is a covariance ratio. Okay, so but we have access with the help of this command, that is the name of the variable in which we have the data, and then we are accessing the residuals. Okay, comma, and then we are saying that residuals and comma, and then we are saying show us these data sets. Okay, because over in this particular variable we have these answers of these residuals. Okay, now we are going to assess the book distance, leverage, and covariance. Basically, against this one, it is also showing us book distance against these data points only. Okay, not against everyone with the help of this particular command, leverage value and covariance ratio. So as you can see that from the book distance, none of the data points, although their standardized residual is greater than +2 and less than -2, but we can see that none of the book distance is greater than 1, so there is no need to delete these values. Similarly, let me talk about that. If you can see that almost none of the head value, or you can say the leverage value, is crossing those limits. So some of them, I believe 169, and this one is near to the lower or upper limit. But as we have discussed earlier, that because none of the book distance is crossing the value of greater than 1, so that means there is no need to delete a particular case. Okay, so once we have checked the, you can say, test regarding the case wise, so which means there is no need to delete any particular data point from our data set. Okay, so this regression model is good enough, so there is no need to delete the data. But now we need to check further two more things. One is whether the errors are independent or not, whether the errors are normally distributed, and homogeneity. So let's first discuss the independence of the error of the regression model. So for that we are going to apply the Durbin-Watson test. Okay, and what is Durbin-Watson? Basically, Durbin-Watson says he is basically looking the serial of correlation, which is known as autoregressive order 1 correlation. Okay, so the assumption is that the errors are normally distributed, the errors are stationary. So what Durbin-Watson test is going to test whether H naught, no first order autocorrelation. Okay, so there should be no first order autocorrelation. Okay, there should be, this is basically between the errors autocorrelation. Okay, so H naught is there is no first order autocorrelation, alternative is there is a first order autocorrelation. So this is the formula of the test statistics. Okay, which we can apply while we are applying the Durbin-Watson test. And the value of this Durbin-Watson test, if it is 2, that means there is no autocorrelation. If it is between 0 to 10, then we can say this is a positive, or if it is 2 to 4, then there is a negative autocorrelation. Okay, so normally the rule of thumb is if the Durbin-Watson test statistics is lying between 1.5 to 2.5, then we will say it's relatively normal. So that means there is no need to worry. Okay, which means there is no autocorrelation exists. Okay, If values are outside this range, that is a cause of concern. So field 2009 suggests that if it is under 1 or more than 3, then definitely we have a cause of concern regarding the error. Okay, that means errors are not independent. So we have to check this thing. So how we can do that? That is with the help of Durbin-Watson test. So for that, we first of all need to install the library called, you can say, package car, and then we are calling it. So whether you can use this function or whether you can use GWT or a Durbin-Watson test, okay, and the name of the variable. So again, as you can see that the p-value is greater than 0.05, so we will say except h naught. Except h naught means there is no first order autocorrelation exists. So that means errors are independent. Okay, and lastly, in order to check the normality as well as the homogeneity of the variance, again I'm using the plot. Okay, that is against residual value versus the fitted value. This is the same plot which I have used in the book distance. So instead of which c is equal to 4, I am using which c is equal to 1. So if I run this command, so in a plot, so let me run it again. Okay, this is basically residual versus fitted value. So as you can see that there is no specific trend we can see. So if there is a trend like that the residual and fitted values start increasing or start decreasing, so there is a scatter form. So which means we can say that there is no you can say there is a homogeneity in the variance. So variations are constant over the fitted value and as well as the residual values. So in order to check the normality, so we can use the QQ plot as well as the scale point. Okay, so basically the QQ plot is indicating the normality of the data. It seems that the data is not, mean error data is not normal. But if you see this particular data set, this data set is quite huge. So which means, so as most of the people say that if data is large enough, we can relax this assumption. Okay, but whereas if we are talking about the scale, the location point, which is giving the same answer which the residual and the fitted value, which is mean this is also talking about the homogeneity of the variance. Okay, because in residual and fitted we are using the fitted value and the normal residual, whereas in scale location instead of using the actual residuals they are using standardized residuals. So still we cannot see any particular trend, it's constant over the time. Okay, now, let me show you some graphical as well. So right now I'm using another data set which is an exam anxiety data. So let me read this data set. Okay, and over here we have the exam anxiety and the exam performance. Okay, this is anxiety variable exam, and now I'm applying the regression model while having the dependent variable anxiety, the independent variable exam. So basically, I'm now basically showing you the graphically scatter plot and the regression using the library ggplot. So this is basically the ggplot between the exam anxiety and exam performance. If I want to fit the linear regression line with the help of ggplot, the answer is over here with the help of this particular code. Okay, so let me run it. Okay, so now as you can see that it is showing me this linear regression line. So they are saying that exam performance percentage with exam anxiety having the negative relationship. So over here I have mentioned that the residuals standard error is false. So but in over here I have removed that one, which means this is true. So if I run it, so what effect I can see, it is also showing me the standard error of this regression line. Okay, so with the help of this one, okay, now basically I'm changing the colors with the value of alpha is equal to 0.1. So if I want to find out with the help of a particular variable, right? Right now, this is indicating between only the exam anxiety and exam performance. But with the help of this particular command, I am coloring with the gender. That means I want to find out the regression model with respect to female as well as male. Okay, so if you want to interpret it, uh, we have already discussed this thing in our correlation lecture, that we can see that whether it's a male or a female, so basically gender is not creating any problem or having any effect. So exam anxiety and exam performance having equal effect on whether it's a male or the female. Okay, similar kind of relation. Multivariate regression model using R. First of all, we will discuss what is a multiple linear regression model, how we can estimate the parameters of the multiple linear regression model using the method of least square, and then I will discuss about the model fit, means how good the particular model is and whether this goodness of model is significant or not with the help of ANOVA test. Then we will talk about by fitting the multiple linear regression models like model 1, 2, 3, 4, and out of that which model is the best model we can use to predict our response variable. We also talk about the standardized version of the parameters. So here we will estimate the parameters, and then we will also talk about their standardized version of the parameters, okay, which we will going to estimate through R, and then we will see how we can interpret those standardized parameters of estimates. And then we will check the accuracy of the regression model. First of all, we will see whether is there any particular case, or you can say the data point, which is basically disturbing the regression model. Okay, if there is, then we will try to delete that case or the data point, and after deleting it, then we will fit the regression model. Okay, so once we have cleared this point, then we have to assess the number of properties. Number one, the errors must be independent, okay, through the Durbin-Watson test. Then we will check the multipolarity between the independent variables. If there is the multipolarity, then model is not good. So we have to make sure that there should be no multipolarity. So with the help of VIF, which is called as variance inflation factor, okay, and then we will check the normality of the residue as well as the homogeneity of the variance. So let me first of all start with what is the multiple linear regression model look like. So here we have a multiple linear regression model in which we have one dependent variable and we have multiple independent variables. And remember that whether we are talking about the simple linear regression model, whether we are talking about the multiple linear regression model, your dependent variable must be the quantitative variable or a numerical variable. It should be measurable form in an interval scale or a ratio scale. Whereas your independent variables must be also the quantitative variable, but it also could be in a attribute form. Okay, how we are going to deal those attribute type of variable we will discuss later. But first of all, let's assume that your independent variables also the quantitative variables. Okay, and our objective in the regression model is we want to minimize this random error. Okay, so we want to minimize this random error by using the method of least square approach. Okay, how we can do that we will discuss later. So remember that this is y-intercept, these beta 1, beta 2, beta k are the population slope. This is your random error, and once we have estimated those parameters, we can represent with beta naught, b1, b2 up to bk, or we can represent with beta naught as an estimated value, beta 1 as an estimated value, and so on. Okay, now the question is how we can do this. So we want to estimate the parameters of beta naught, beta 1, beta 2 up to beta k. So first of all, let's discuss that how the regression model look like, mean how the data look like in the multiple linear regression model. So we have y, that is a dependent variable, we have k independent variables. Okay, the dependent variables values are the measurable values, as well as the independent variables are the measurable values, or we can say these all are the column vectors. Okay, so we can represent this one is with the help of summation j1 to k bj xij plus error epsilon I. Okay, so where I is representing basically the equation number, j is representing in a particular equation the variable, or you can say j is basically representing the particular variable or a column, I is basically representing the row. Okay, so that is basically the observation perspective. Okay. Now the ultimate target is we want to minimize this one. So first of all, how we can calculate the epsilon? That is the actual value minus the predicted value. Okay. So this is the epsilon, or you can say residual or error. So we want to minimize the sum of square of error. Okay. So by putting y hat in place of y hat, we can put the value of this one, that is equal to this one. Okay. Now if I'm going to differentiate with respect to beta naught and put it equal to 0 and try to find out the value of beta naught, that is basically, if I am just simplifying this one, this would be equal to this equation. Now if I'm going to differentiate with respect to beta 1, I'm going to get this equation by placing it equal to 0. And then if I'm going to differentiate with respect to beta 2, then I'm going to get the third equation. Then if I'm going to differentiate with respect to beta k, I will get the last equation. Now if we simultaneously solve these equations, we would be able to get the values of beta naught, beta 1, beta 2 up to beta k. So the similar thing we can calculate with the help of matrices. Okay, how we can do that? Okay, the same equation we can write down this way. So where is y is the column vector, x is basically n by m matrix. Okay, and b naught is the column vector, and similarly epsilon are the column vector, right? Okay, so now basically these ones are basically represented with beta naught value. Okay, so these are basically the constant number, whereas x1 is representing this one, x2 up to xk. Now, in order to find out the values of the beta naught, beta 1 up to beta k, we can represent the normal equations which we have shown over here. So these are called as the normal equations. So how we can represent them, those equations in the form of matrices like this way. That means x transpose into x. So if I take the transpose of this matrix and multiply itself, I will get this value, and then is equal to x transpose into y. So I will get this one. Okay. So by multiplying x transpose into x, I will get this matrix. Then this is basically beta's value. That is basically this one. We want to estimate this one. And this is basically equal to this one. Now, in order to calculate the value of betas, okay, what we need to do is we will try to find out the x transpose x inverse, okay, because it is going to be divided by this one, and then x transpose y. Okay, so that would be the formula to find out the values of beta naught, beta 1 up to beta k. But obviously we are not going to discuss how we can do that manually, so we are going to discuss how we can estimate these values, the values of these betas, with the help of R. So for that, I'm going to use the data set of album sales. So where the dependent variable is sales, whereas the independent variables are the advertisement expenditure. So we have the airplay and we have the attractiveness. So this is the amount we are spending in thousands basically, okay, in the advertisement expenditure in thousands of pounds, right? Whereas airplay is basically the number of times the song from the album are played on a radio during the week. Similarly, attractiveness is basically the attractiveness of the band, which is basically from 0 to 10. We have scaled it up, and the 10 is basically indicating the more attractive that particular song is. Okay, so now let's fit the regression model using R. So how we can do that? So let me open the R code. Okay, so here we have the code for the to assess the data set. Okay, so I'm saying that read.delme, basically we have the data in DAT format. Okay, you can say in the text format. Okay, so header is equal to true means the first row would be considered as the name of the variables. So if I run this one, because we have the data set in the same folder in which we have created the project. Okay, so if I am going to run this one, okay, right now it is assessing it. Okay, as you can see that right now we have this data set, we are reading it. So in order to view this data set, we have a command capital V I E view, then we can use album2. Okay, and then if I'm going to run this command, we can see this data set. Okay, now, in order to find out the regression model, so first of all, what I am going to do is I'm going to fit only a simple linear regression model where we have a dependent variable sales, where independent variable are the advertisement expenditure. Okay, that is this one. So with the help of LM sales tilde sign, that is this is the dependent variable, this is independent variable, this is the tilde sign. Okay, and then data is equal to the name of the variable in which we have stored the data set. So now if I run this command, so after running this command, so what R will do, it will run the simple linear regression model and save the result in this particular variable. So in order to see the result, we have to run this command summary and then in the name of the variable in which we have stored the results of the linear regression model. So as you can see that this is the value of beta naught, this is the value of beta 1. With the help of t-test, we can check that whether the results of these betas are significant or not, because both the p values are less than 0.01 even, so it is highly significant. So we can say that advertisement expenditure is significantly affecting the sales dependent variable. Okay, or we can say that with the help of R square, that 33% of the variation in the sales is due to the advertisement expenditure, right? That is basically I am talking about this one, as well as the parameter estimation. So let me show you through with the help of even this one. Okay, uh, that is basically this one. So we have run the first model. Okay, let me run the second model first and then I will show you the result. So the second model we have fitted, that is we have the dependent variable sales and then we have three independent variables. We have advertisement plus we have airplay, we have attractiveness, and the data is equal to album2, and we are going to store this result in the variable album sales dot 3, and then we are going to see the results. Okay, now we have the results of album sales 2 as well as album sales 3. Okay, so now let me show you the two models result. Okay, first of all, we have model 1 when we have one dependent variable and one independent variable. Model 2, again, obviously, we have one dependent variable and we have three independent variables. So let's first discuss regarding the model fit, whether how much variation in the sales variable this independent variable is able to explain. Similarly, how much variation in the dependent variable these variables is able to explain. So with the help of R here, we can say that 33.45% of the variation in the sale is due to the advertisement budget, or we can say that 33.46% of the variation advertisement budget expenditure is able to explain in the sales variable. Okay, whereas in model 2 we can see that the R square value is 66.47%. So that means the advertisement budget, airplay, attractiveness is able to explain 66.5% of the variation in the album sale. Okay. Now we want to test whether these models are significant or not, mean significantly good fit models or not. We will check model 1 as well as model 2. Right now we are not talking about which one is the better one. We are just checking whether the model 1 is significant, which means whether attractive advertisement expenditure is significantly able to explain the variation in the sale. Similarly over here, whether advertisement expenditure, airplay, attractiveness is significantly able to explain the variation in the sales. So how we can do that? we can do that with the help of ANOVA test, where H naught is look like this one. This is basically the H1, okay, where at least one of the beta j's is not equal to 0, okay, and this is basically the formula, but in R we are getting these results. As you can see that model 1 as well as model 2, both the models have test statistics against that the p-value is less than 5%, okay, so we will say that these models are significantly fit model or a good model in order to explain the effect on the sales of these independent variables, whether we are talking about the model 1 or whether we are talking about the model 2. But now the question is, which one is the better one? Okay, whether model 1 is better, whether the model 2 is better. So for that, we again apply another F test statistics, okay, which would be able to tell us whether the model 1 is the good fit for this particular data set or whether the model 2 is good fit. So this is known as the model comparison in hierarchical regression. Why we are saying hierarchical regression? Because first we develop a linear regression model only with one independent variable, and then we have developed with the help of three independent variables. So you can incorporate if you have more variable, like model 3 we have developed with the help of two variable or a four variable if we have, okay. So now I want to check whether the model 1 is the better one or whether the model 2 is the better one. Okay. As you can know that model 1 is basically we have the dependent variable and only one independent variable, whereas the model 2 we have the dependent variable and three independent variables. Okay. And in R, basically we have a function called ANOVA. In this particular variable we have basically fitted this model. In this particular variable we have fitted result of having this model, and once we get this result, so with the help of this p-value we can easily say that because it is less than even 1%, we will reject h naught. Reject h naught means model 2 is significantly better than the model 1. Okay, basically what R is going to do is it is going to compare the R square of the two models, and it will say that whether in model 2 R square is significantly improved compared to model 1 or not. So as we have seen that because the p-value is less than 1%, so we can say that model 2 is significantly better fit compared to the model 1. Okay, now let's discuss about the parameter estimation. Okay, first of all, once we have run this model 2, that is basically sales and advertisement expenditure, airplay and attractiveness, we got the parameter estimation. This is the value of beta naught. Okay, this is the value of beta 1, beta 2 and beta 3, right? Because we have the budget in thousands pounds perspective. Like right now we can say that how we can interpret this advertisement budget expenditure, that basically it is saying that for every 1000 pounds spent on the advertisement expenditure, an extra 0.085 thousand, which means albums are going to be sold, which means 85 albums are going to be sold by spending 1000 pounds on the advertisement budget expenditure. But remember that this would be only true if we are going to assume that the effect of the attractiveness and the airplay effect is going to be constant. Similar interpretation is for airplay, similar interpretation for the attractiveness. Okay. Now, in order to check the significance, so we are going to check the values of the p. Okay, because all the p values are less than 1%, so we can say that the effect of advertisement expenditure as well as airplay as well as the attractiveness is significant on the response variable, which is a sales variable. Okay, so there is another way to check whether these variables are significantly affecting the response variable, okay, or not. So with the help of confidence interval, so we can also check this one. That is because right now we are calculating 95% confidence interval. So if you are interested to find out the 99% confidence interval, So what would be the command? That would be call int album sales to and level is equal to 99. So now it is going to show us the 99% percentage of the confidence interval. Okay, so if the value of 0, which means if I'm going to check whether the advertisement variable is significantly affecting the response variable or not, because for that the h naught will be the beta 1 is equal to 0, whereas alternative would be beta 1 is not equal to 0. Similarly, for airplay, h naught will be beta 2 is equal to 0, whereas the alternative is beta 2 is not equal to 0. For attractiveness, h naught would be beta 3 is equal to 0 and alternative would be beta 3 is not equal to 0. If the 0 value is lying within this confidence interval, we will say accept h naught. If 0 value is not lying within this confidence interval, we will say reject h naught, because in none of for these variables the 0 value is lying within these confidence interval. So we can easily say that we should reject h naught in all three cases, which means advertisement expenditure, or you can say advertisement budget, has significant effect on the sales. Similarly, airplay has a significant effect on the sales. Attractiveness has a significant effect on sales, right? Now, once they have the significant effect, we can check from the values of these whether these effects are positive or negative. As we can see that this is a positive effect, this is also positive effect, this is also positive effect. So which means by investing more and more on the advertisement budget or expenditure, we will able to increase the sales. More the song is going to be played on a radio, okay, higher the sale will be for that particular album, and so on. Okay, now let's calculate the standardized versions of these regression coefficients. So these are basically the normal estimation of the you can say parameter estimation of the regression model. Now we are going to calculate the standardized version of the B. And what's the difference? Basically, the normal parameter estimate of the regression model are depend on the unit of measurement of the variable, whereas standardized variables are not depending on the unit of measurement. And how we can interpret those ones? The number of standard deviation by which the outcome variable will change. As a result, one standard deviation change in the predicted or the independent variable, which means first of all what we are going to do is we are going to calculate the standard deviation of the dependent variable, we are going to calculate the standard deviation of the independent variables. Okay, so once we have, I believe I made some mistake over here, so we have to use the, I believe, album 3, right? I think so. Okay, so depending upon in which variable we have stored the data, whether 2 or 3. Okay, so the name of the variable, let me check. We have, okay, album 2, yes. Okay, so we have stored the data in album 2 variable. Okay, so now we are going to find out the standard deviation of this particular variable. We have find out the standard deviation of this variable. We have find out the standard deviation of this variable. So let's discuss first of all how we can calculate the standardized coefficient of the regression model using R. So for that we have to use this package. Okay, and then we are going to use the function lm dot beta and then the name of the variable in which we have the fitted regression model, that is album sales dot 3. So these are, this is beta 1, beta 2 and beta 3, and these are the standardized betas. Okay, how we are going to interpret? As I told you that first of all you must calculate the standard deviation values in order to understand the interpretation of this one. So let's interpret it. So what does this particular value mean is that if the advertisement budget expenditure increased by one standard deviation. So one standard deviation means what? That means we are going to calculate the standard deviation of the advertisement expenditure, and that is this one. So this is one standard deviation. That means equal to this one. So that, which means if I'm going to increase the investment in the advertisement budget is this amount, that is the one standard deviation of the advertisement budget. The album sales will be increased one standard deviation. Okay, so one standard deviation means right now the value of the beta is basically 0.511. So that means 0.511 standard deviation of the album sale. And what is the album sales? That is this one. So 0.55511 multiplied by the standard deviation, this one, that is this one. So in short, we can say that on spending the amount on the advertisement budget is equal to this one, the sales will be increase of the album is this one. Okay. Again, if we are going to make sure the effect of other variables are going to be constant. Okay. So this is true only if the effect of other variables are constant. So I hope you got the idea how we are going to interpret the standardized version of the B values. Okay, now let's find out whether this regression model is accurate or not. So for that, first of all, we need to check is there any particular data point which may affect this regression model. So for that, we can calculate the standardized residual, Cook distance, leverage value, and covariances. Okay, so let me calculate this one through R first. Okay, uh, this this is it. So with the help of this command, I am going to calculate the values of standardized residuals. Okay, that is R standard and the name of the variable in which we have the fitted regression model. Okay, I am going to store it in this particular variable. So with the help of this command, we have calculated the standardized residual. With the help of this function, we have calculated the Cook distance. How we interpret this one, we will discuss later. With the help of this one, we are able to calculate the hat values, or you can see the leverage value, and the last one we have able to calculate the covariance ratio. And then with the help of this command, I'm going to store this data set into the album 2. Okay, that is right. And then I'm saying round. Okay, now basically up to 3 digits. That is basically we have stored all the data set in the name of the variable which is album 2, in which we have the actual data set. So we have the actual data set as well as we have the values of standardized residual, Cook distance, hat values, and ratios. Okay, what are the criteria we have studied in when we were talking about the simple linear regression model? Like one of the criteria, if the standardized residual are greater than 2, try to find out those points. So how we can do that? So we are saying that album 2 standardized residual greater than 2 or standardized residual is less than -2. So if I run this one, so I can find out wherever you are finding the value 2, which means that data point is either greater than 2 or less than -2. If it is false, that means it is lying between -2 to +1, +2. Now, in order to find out, like we are going to store this data set, again, this entire command in a variable called album2 large dot residuals. Okay, so I'm going to run this command by storing the result in this variable in order to sum, like how many variables are basically out of this range. So there are 12 values that are out of this particular range, and then now what I am going to do is I am going to you can say call the data from the album 2. The album 2 those are having the large residues, mean only those data points should be shown to me which having the large residuals. So which one? Which having the standardized residuals are either greater than 2 or less than -2. So I want to see sales variable, airplay, attractiveness, advertisement, as well as the standardized residual. So let me run this command. So with the help of, we can see that all the 12 data points. So data point number 1, 2, 10, these are having the standardized residual either greater than 2 or less than -2.2. Now, what we need to do is we want to calculate the Cook distance, leverage value, and covariance ratio. We have already calculated this one. So we only want to see against these 12 data points the values of hook distance, leverage value, and covariance ratio. So how we can do that? Album 2 and then the name of the variable in which we have the largest standardized residuals means all the data points which having the standardized residual greater than 2 or the less than 2, and then we are saying that we want to see against those data points hook distance, leverage value, and covariance ratio. So let me run this one. So these are the hook distance. So let me interpret this way. Okay, so first of all, we have seen that these 12 data points having the standardized residual either greater than 2 or less than minus 2. So we have calculated the hook distance, leverage value, and the covariance ratio. What's the interpretation? If any of the data points hook distance is greater than 1, then we can say that that particular case may influence our regression model, because none of the data points having the hook distance is more than 1. Okay, then we can say that there is no need to delete any data point from the data set. Similarly, in order to interpret the leverage value, because it is also giving us the same kind of information. So what's the interpretation of the leverage value? That is basically the average leverage value we have to calculate. So how we can do that? That is k plus 1, where k is the number of independent variables. So in our case, that was 3. Okay, so these are the 3 independent variables plus 1. So 4 divided by n is the total number of observations. So we have the 200. So 4 divided by 2, this is basically the average leverage value. Okay, then the criteria is we have to calculate the twice, and this is a twice, mean multiply by 2, as well as thrice and 3 times. So multiply by 3, that is this one. If the leverage value is lying within, you can say this range, okay, then we can say that there is no need to delete any particular case. As you can see that all the cases within the boundary of the 3 times of the average, which means all the values are less than 0.06. Okay, only the case 1 is basically closer to the 2 times. Okay, so we can say that there is no need to delete any particular case, or either you can use the covariance ratio interpretation. Okay, so for that we need to calculate the upper limit, we need to calculate the lower limit with the help of these formulas. If the covariance ratio is lying within this range, okay, we will say there is no need to delete any particular data point. If it is crossing, then we can think on that one. Okay, but remember that for deleting a particular case, in that case you can only check the cook distance, because none of the case having the cook distance is greater than 1. So we can say that there is no need to delete any particular case or the data frame. Okay, now we need to check whether the errors which are we are getting after fitting this regression model are independent or not. So for that, this assumption can be checked with the help of Durbin-Watson test, in which h naught, the row is equal to 0 and alternative is row is not equal to 0, which means there is a first order autocorrelation, whereas alternative is there is no first order autocorrelation, there is a first order autocorrelation. So how we can do that? We can do that with the help of this command. So I will run it. Okay. The rule of thumb is if the Durbin-Watson test value is lying within this range, then we will say it's a normal. Okay. But if it is greater than 2.5 or less than 1.5, then there is a case to concern about it. Like even field 2019 says not only 1.5, if it is less than 1 or greater than 3, then there is a case of concern. So let me run the Durbin-Watson test in R. So for that we need a package called car. Okay, and we can run. Either you can use this particular function, okay, or either you can use the second one, DWT. So both are fine. So in both the cases, we can see that the Durbin-Watson test values are lying within the range of 1 to 3. So that means there is no need to delete, or that you can say errors are independent. So the next thing we need to check is the multicollinearity. whether there is a multipolarity in the data set or not. So how we can do that? That is with the help of variance inflation factor, and how you can calculate that is this one. So normally the main idea is they are saying if the variance inflation factor is greater than 10, then there is a multipolarity existing. If the variance inflation factor is less than 10, there is no multipolarity in the data set. Okay. So I have calculated the variance inflation factor with the help of this particular function. I will also run in R and show you. As you can see that advertisement budget, airplay and attractiveness. Against all that, we have variance inflation factor less than 10. That means there is no multipolarity exists. Okay. Or you can say if there is one, that means there is no correlation. So there are multiple type of interpretations are available. Like the average variance in inflation factor greater than one, the regression is biased. Okay, if the average, so that is basically we can calculate that one. Okay, but normally people are mostly using this particular interpretation that if the variance inflation factor is greater than 10, then there is a cause of concern, but if it is less than 10, then there is no need to worry. Okay. Similarly, we can also find out the tolerance, that is basically 1 over VIF. Okay, so that is basically zero point 0.1, or we can say that is if the tolerance limit is greater than zero point 0.2, then there is a problem. Okay, so in our data set, there is no multipolarity exists within our data set, as we can see that even through R, when I am running this VIF function, so the values are, all the values are less than 10. Now let's calculate the VIF through in R. So how we can do that? That is with the help of this function. So if I run this one, so as you can see that all the VIF are less than 10. So that means there is no multipolarity exist in our data set. Okay. Now, in order to check the other assumptions such as the normality in the data as well as the homogeneity in the errors, so we can use this plot function, and if I enter, we can get the value plot of residual versus fitted. We will get the plot of normal QQ plot and scale location plot. Okay, so with the help of this one, how we can interpret whether there is we can say that as you can see that because there is no trend between the residuals as well as the fitted value, so we can say that there is no heterogeneity in the variance. So that means the variance between the residual and the fitted values are constant against every data point. Similarly, the data seems to be normal, means the residuals are data seems to be normal. Similarly, the scale location, because the difference between the residual versus fitted and the standardized, or you can say scale location, is in the residual versus fitted, we are using the residuals of the residuals as well as the fitted value. Whereas in scale location, we use standardized residuals versus the fitted. So these two graphs are giving us the same kind of information, because that the variation against every fitted value, the standardized residue, the variation in the standardized residue is almost same, or you can say constant against every fitted value. So we can say that there is a homogeneity. So if there is a particular trend, then we will say there is a heterogeneity exists, or you can say the variances are not constant. Because right now the variances against every fitted value is almost same, means the variation is almost same, then we can say that there is only a homogeneity exists. I hope you got the idea how we can perform the multiple linear regression model in R and reverse regression analysis using R. So when I am saying the reverse regression analysis, which means I'm talking about the bootstrapping perspective. So what is the bootstrapping? As we have discussed in our previous one of the previous video when we were talking about the correlation analysis, that bootstrapping is basically the with replacement sampling technique. Okay, so we generate the multiple with replacement samples. However, your assumption of the normality and the homogeneity can be relaxed. Specifically, if we are talking about the regression analysis, as we have discussed in our previous video lecture, that one of the multiple linear regression models assumption is that is to check the assumption regarding the residual that it should be normally distributed and the variances of the residual must be homogeneous, whether we are applying the simple linear regression or whether we are going to apply the multiple linear regression. So let's say if those assumptions are failed, then in that particular case, what we can do? So in that particular case, we can apply the reverse regression, mean we can apply the bootstrapping technique on the multiple linear regression. So for that, I'm going to take the example of the same which we have discussed while we were talking about the multiple linear regression model, in which sales is basically the dependent variable, whereas advertisement expenditure was the independent variable. Another independent variable is airplay and the attractiveness. Okay, so this is basically the budget amount which we are spending on the advertisement. Airplay means the number of times the song from album are played on a radio. One, attractiveness is basically ranked from 0 to 10, where 10 means the song is very good. Okay, so for that, first of all, before discussing the bootstrapping, let's read this data file, which I have already in my you can say the folder or in my project folder, which I have created for the multivariate linear regression. Okay, the data file is with the extension of .dat. Okay, so once I run this command, with the help of this command, I would be able to read the data file, and header is equal to true mean the first row would be considered as the name of the variable. So once I have run this command, now I am assuming that one of the assumption is failed. Okay, so I want to apply the bootstrapping, okay, with the 200 application. So for that, first of all, when I am going to apply the reverse regression, mean the bootstrapping technique, I need to write down a function. Okay, so I'm writing down a function in which I'm giving the three parameters. Why I'm giving the three parameters? Because I'm applying the bootstrapping for the multiple linear regression model and I need multiple test statistics. Okay, so for that, first of all, I need the multiple linear regression formula, okay, which means y is equal to the multiple independent variables. So we are going to input that particular formula in this particular variable, which is I am calling as formula, and then in the data variable, or you can say in the data object, I am going to store the data file, okay, on which I want to generate the samples, and I is that is basically representing the number of replications. Okay, so these are the three arguments we have needed for this particular function. Now I am going to define that in D variable store those applications, okay, which we have generated using the bootstrapping technique from the data. And in a fit variable, I am going to apply the linear regression model using the formula. Okay, we are going to define this formula further when we are going to call this function. So in formula, I will write down the formula of the linear regression model, and what is the formula we'll discuss later. And then in data, I am going to indicating that select the data D. So every time it is generating the with replacement sample, it is going to be stored in D, and every time for every sample it will generate a data. Okay, and then I want to return from this function that it should show us the coefficient fit. Okay, that is basically you can say beta naught, beta 1, beta 2, beta 3, whatever the independent variables are. Okay, so first of all, we have to define this function. Okay, so we have run this function. Now we want to call this function. So this is the definition of the bootstrap function, which we have stored in the boot reg variable. Now I'm going to call this function. So for that, I'm saying boot results. That is the name of the variable in which we are going to store the results, and then the function we are using, that is boot, and in statistics we are mentioning the name of this variable, which is basically where we have defined the entire function. So we are calling this function, and from this function we are saying this argument is equal to sales, that is a dependent variable, tilde sign, and we have the three independent variables. One is the advertisement expenditure, airplay, and the attractiveness. Okay, and then we are mentioning this data. So what is the data? That is the name of the variable in which we have stored the data. That is basically this one. Over here we have read the data. So in album 2 variable we have the entire data set. Okay, and r is equal to 2000 mean, that is basically over here I, that is the number of replication. So how many times we want to replicate it. So if I am going to run this command, now we have performed the bootstrapping. Now in order to see the results, I am using a function called boot.ci, that is basically showing us the confidence interval of what, that is a boot results. So that is the name of the variable in which after the bootstrapping the results are stored, and I am going to see the results with the criteria BCA, which is called as Bayesian criteria. Okay, so with the help of this Bayesian criteria, I want to see the results of the bootstrapping. Index is equal to 1 mean, I want to see the results of beta naught. Okay, that is basically the intercept. So these are the results. Okay, how we are going to interpret it, I will talk about later. But let's see if I am going to apply other criteria. So you can also apply all. Okay, or either you can apply normal, or either you can apply the percentile. Okay, but with the help of all, we would be able to apply all the criteria available in this particular function, which is normal. With the help of normal, what is the confidence interval? With the help of basic, what is the confidence interval? With the help of percentile, as well as with the help of Bayesian information, Bayesian criteria. Okay, so with the help of these, similarly, because we have the three independent variables, so with index is equal to 2 mean, we are going to apply the Bayesian criteria for beta 1, and we are calculating the confidence interval similarly with the help of 3, beta 2, and beta 3. So now how we are going to interpret it. So first of all, what I have done is I have find out the confidence interval, okay, which is generic confidence interval for beta naught, beta 1 up to beta 3, okay, which is in which we are saying that the data follow the normal distribution, okay, that is basically the residue, the normal one, okay. Now once with the help of this particular function, I have calculated the Bayesian criteria, with the help of Bayesian criteria, the confidence interval. Similarly for beta 1, beta 2 up to beta 3. So as you can see that if you compare these confidence intervals with the actual one, okay, with the actual one, you can see that for this particular data set which we are using for the album sales, so these bootstrapping confidence intervals and these confidence intervals are not different from each other. So we can say that that means normality is not the issue in this particular data set. Okay, because all the confidence intervals are closer to the actual confidence intervals. Okay, so that's where the normality is not an issue. Okay, but if there is a normality is issue, so still we can use this bootstrapping, and how we can interpret that one, like if I want to interpret whether the beta 1, the beta 1 is basically representing the first independent variable, which is basically we have used advertisement, okay, over here, that is the advertisement expenditure. If the value of 0, because over here our h naught is beta 1 is equal to 0, and alternative is beta 1 is not equal to 0. What does this mean? That means the advertisement expenditure has no effect on the sales, okay, by making the other factors constant. Whereas this means the advertisement budget expenditure have the effect on the sales. So whether we have to see that is this particular zero value is lying within this confidence interval or not. If 0 is lying within this confidence interval, we will say except H naught. That means the advertisement budget expenditure has no effect on sales. Because 0 is not lying in this particular range, so we can conclude that the advertisement budget expenditure has effect on the sales. okay, because 0 is not lying within this range. Same is the case for the airplay, same is the case for the attractiveness. So all three factors are significantly affecting the sales. Okay, so I hope you got the idea how we can apply the reverse regression analysis, which means how we can perform the bootstrapping on a multiple linear regression model using R. So think regression analysis using R, but when we have the categorical predictors, or we can say the categorical independent variables. So in order to deal with the categorical independent variables, we can take the help of the dummy variables. What the dummy variable mean is we are going to code that categorical variable. Okay. So coding means, like, if for example, if we have the two level category of a variable such as male or female, on or off, yes or no, okay, defective, non-defective, then we can code that particular variable as 0 or 1, okay, as a dummy variable. For example, another example we are considering over here is if we have a dependent variable is a teacher's salary, which we are representing with y, okay, and the dummy variable which basically is indicating whether we want to see that on average the smoker teacher has the more salary or a non-smoker teacher has a more salary. Okay, so we have represented a non-smoker with 1, okay, we have coded it, and the smoker is with respect to 0. So graphically, if we are going to represent this one, so right now if this is 0, so which means this is alpha, which is basically representing the salary of the smoker person. Okay, that is the average salary of a smoker person. So this alpha is going to be represented. Whereas if this is equal to 1, then alpha plus beta is going to represent the average salary of a non-smoker teacher. So as we can see that from this particular graph, so that the on this particular scenario, the non-smoker teacher has the higher salary on average. Whereas if we have such a variable, such a categorical variable in which we have more than two levels, then how many number of dummy variables we needed? That is going to be the number of levels minus 1. So we will discuss later, but let's first discuss that if we have a categorical independent variable and it has two levels, how we are going to deal in R, and then how we can interpret those results. Okay. So for that, let me open the R. Okay, so that is the regression analysis. So I'm going to use the built-in data set. Okay, so first of all, for that I need to call a library called car data. So if you haven't installed it, so first you need to install, then I'm going to call it. Okay, so in this car data set we have a data set called as salaries. Okay, so now I'm going to, with the help of this view command, I'm going to see the data set in the salary. Okay, so where we have the ranks of the professors, so from which discipline they have related with, whether the discipline A or B. Okay, and then years since they have got the PhD, service, okay, that is basically the experience, their gender, their salary, and so on. Okay, now we are going to, with the help of this command, as you can know that with the help of head command, we can see the first six data sets. Okay, so if I write down comma 8, so you, with the help of this particular command, you can see the first 8 data entries. Okay, by the way, first of all, because we are interested to find out that is the gender, or we can say sex, has the effect on the dependent variable, which is basically the salary, whether male having the more salary or whether female having the more salary. So for that, I'm going to fit the multiple simple linear regression model. Okay, but our independent variable is because it has the categorical variable, so we have to first code this dummy variable. So in with the help of R, how we can do that? We can use the function called contrast. Okay, and then salary, that is the name of the data set, or you can say the name of the variable in which we have the entire data set, that is salaries, dollar $sex. If I run this one, okay, so you can see that R automatically coded that variable, okay, where 0 is representing female and one is representing male. Now, in order to fit the simple linear regression model, so the function will remain same, which we have discussed while we were talking about the simple linear regression model using R. So for that, the function is LM, which is a linear model. This is our dependent variable. This is our independent variable, and data is equal to the name of the variable in which we have the data set. So if I run this command, and then in order to check the result, we have to use a function called summary, okay, and then the name of the variable in which we have the fitted model. So as you can see that this is basically the average salary the female professors are getting, whereas female teachers are getting. This is the how much salary the male is getting more than the female. So we can say that these are the significant results because the p-values are less than uh, um, um, almost equal to zero. You can say less than 1%. So these are the highly significant results that on average male teachers are getting more salary. So let me show you through PPT as well. Like the average salary of the female is equal to this one. So the average salary of male would be alpha plus beta as we have discussed in our previous slide. That is basically this non-smoker perspective. So that would be this estimate plus this one. So that would be the average salary of male. And we can easily say that because are showing us that these are the significant effects. So the male is getting significantly higher salary compared to the female. Okay. Now let's discuss if we have more than we have a dummy variable which has more than you can say two levels. Okay. So for that, I'm going to use basically the rank in which we have the three levels. One is assistant professor, associate, and professor. So if a particular variable has more than two levels, so in order to check how R has coded that variable and converted that variable into the dummy variable. So as you can see that because in a rank variable we have the three categories. One is professor, assistant professor, and associate professor. So that means R is going to be generated two dummy variables. Okay. So remember that as I have shown you that how many number of dummy variables we needed, that is basically the number of levels minus one, because in this particular case we have three levels: assistant professor, associate, and professor. So R is going to be generate two dummy variables. So how we can check that one, that how R has coded that variable as a dummy variable. So for that we can use the function model dot matrix and then started tilde and the name of the variable, okay, which is basically the categorical variable, that is a rank. Then data is equal to salary. So if I run this command and with the help of head, we can see you have to ignore this first column. So they are ranking um, rank associate professor and rank professor. So basically, so R what it has done is that it convert this variable into the two variable, that rank of the associate professor. So in this particular data set, wherever R has found the associate professor, they mention one. As you can see that at the sixth place, it's associate professor. So this is one. So wherever R didn't find the associate professor, so it ranks as zero. Similarly, for the professor, it ranks one. Wherever there is not a professor, that would be zero. Okay. So the third one is the assistant professor. So that is basically would be considered as zero. Okay. So how we are going to interpret that one? So I will discuss in a while. But with the help of this command, if I'm using this minus one, so it will remove this first column. So it will not showing us the intercept, only showing us the rank of associate professor as well as the professor. Then what I'm going to do is I'm going to fit the multiple linear regression model in which one of the variable is, that is year service, which is experience, that is the quantitative variable. Okay, that is basically this variable, whereas rank is basically a dummy variable. Okay, and we have seen that how R has you can say converted to the dummy variable. Okay, And similarly, the discipline is also a categorical variable, sex is also a categorical variable. So R will automatically convert the categorical variable into the dummy variable. Okay. And in order to check how R has converted the dummy into the dummy variable, so we have seen with the help of this function, and if it has only two categories, so with the help of this function. But now I'm going to apply the multiple linear regression model using R, where dependent variable is salary. So now with the help of this model too, so we have fitted the multiple linear regression model. Now I'm going to show the two things. Okay, with the help of ANOVA, you can see the results. With the help of summary, you can see the results. The difference is if I run the ANOVA, it is not showing me the coefficients of the particular. Now you can see the showing me the values of beta naught, beta 1. It is also telling me that whether particular factor, whether the particular independent variable is significantly affecting the dependent variable. So right now it is showing us that rank is a significant factor, okay, that is affecting the salary. Similarly, discipline is also a significant factor. So which means we can easily say that the professor may have the more salary compared to the associate professor. Similarly, the associate professor may have the higher salary compared to assistant professor. But we have to check which rank of the professor getting higher salary or which one is the lower salary. Similarly, some discipline professors getting more salary compared to the other. So how we can check that? That is with the help of this summary command. Now we can see that so basically, the rank of associate professor getting more salary compared to the assistant professor. Okay. Okay. Similarly, this is basically indicating. So that is basically the assistant professor is a control. You can say the variable or the control factor. You can say. Similarly, the rank professor, the full professor is getting more salary compared to the assistant professor. How much that is basically this one. And this is the significant factor, which is the rank of the associate. The rank of full professor is also a significant factor, or you can say getting the more salary compared to the assistant professor. Whereas discipline B is also a significant factor because the p value is less than 1% even, okay, 5% as well as 1%. So which means discipline B professors are getting more salary compared to discipline A. How much? That is this one. Okay. Whereas we can see that the gender is not a significant factor. Okay. Similarly, the year of experience is also not a significant factor. Okay. So let me show you once again. So these are basically the outputs as we have seen earlier. So we have seen that only the rank and the discipline categories are the significant factors with the help of this ANOVA command. And with the help of this summary command, we can see that the associate professor, how much salary they are getting higher than the assistant professor. We also have seen that the professor rank is getting higher salary compared to the assistant professor. How much? That is this one. Similarly, the discipline B's professor are getting more salary compared to discipline A's professor. How much? That is this one. So I hope you got the idea that how we can perform the simple linear regression as well as multiple linear regression when we have the categorical predictors, and how we can interpret the results. So thank you so much. See you in the next video.